So here we are in 2.1. We are looking at exponential and logarithmic functions. Before we get to exponential logarithmic functions, which is supposed to be a review from the prerequisites class, let's take a look at some formulas that you've seen before. Future value, compound interest. I'm looking at the very first one that was introduced to you in a previous class. It's a of t, its function a of t equals p principal times 1 plus r to the power of t. This first one is when you're um, compounding annually, and obviously will have to be given the interest rate and the principal. And this is the formula to figure out the future value. A of t is the future value. All right, the one right next to its more general form, because it accounts for all kinds of different compounding. So it is A of t equals principal, parenthesis 1 plus r rate of compounding divided by n. N is amount. Let me actually write it down. N is number of number of compounding per year. So obviously, if it's annually, that would be 1. So that would lead us back to this formula. But if it's compounding is semi-annually, that would be n would be 2. If it's monthly, n would be 12. If it's quarterly, n would be 4. And so on. It could be daily, which would be 365, and would be 365. So again, these formulas, this is particular one, should be familiar. And the first one is just derivative. The first one is just when n equals to 1. That's where you get. So looking at the example, when you're solving these problems, besides the fact that it's familiar, it's really you have to be careful when you put it in a calculator. Make sure you pay attention to the order of operations, so you actually get the right answer. So they're not complex, but again, everything has to be put in calculator correctly. So here is an example from your textbook. You invested $5,000 for 5 years. Now they already give me t in years, right? If they didn't give me, like, if I was investing for, let's say, 14 months, I would have to express that 14 months in terms of years. You would take 14 divided by 12, and that ratio gives me the amount of 14 months in years. So, but here we already got that t, and then at an annual rate of 3.25. Well, we have to, this is in terms of percent, 3.25%. So we do know that in this case, R is equal, you divide this by 100, and should equal to 0.0325. And you use that number in your formula. Okay, so that's our T, and this is our principal. Okay, and compounded, we need to figure out all for different compounding. So compounded annually, that is n equals 1. Quarterly, that is n equals 4. Monthly, that is n equals 12. And daily, n equals 365. And it's all the same formula. So hold on a second. Let me write it down for you guys. Okay, so here we go. A of t equals 5,000, and the first one is this is um compounded annually. Okay, the second one, so as you can see, it's instead of t, I'm using one. Instead of n, I'm using one, replacing one. This second one is compounded quarterly, and the third one is compounded monthly. Everywhere you see n, I replace it with 12. And the last one is compounded daily, and you just replace n with 365. And that's all to it. You've done these before. They are not super complicated, but they lead to something. We're going to use this formula, and we are going to use some properties of calculus and take a limit and see what happens when we are compounding more often than 365, but 1,000 times a year or million times a year and so on. And this brings us to the natural base. So you have seen E uh, before in the previous class, but now you can define it in terms of calculus. So which you know as a number 2.78281828, irrational number, has no pattern, no ending of decimals, is equal to limit as n approaches infinity of this compounded interest formula. And of course, take a look at a textbook. It writes down all the steps on how you take a limit. But this is our definitions. We need to understand now how we actually arrive at this natural base e, or that number, irrational number e. Okay, so that lead us to continuous exponential growth rate. So if taking limit this 1 plus 1 over n to the power of n is equal to 2.782818, then it makes sense, and it leads us to the continuous exponential growth. Means if your compoundings are continuous, then you can just replace that middle with e, and then you have your final amount is equal to principal times e, that's 2.78 to 8 blah 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 to the power of rate times time. Again, don't forget to express time in terms of years. Let's see, then here's example. The same, you have $5,000 to invest at rate 0.0325 for 5 years, and you just plug it into calculator, and here you go. Then let's take a look at exponential functions. For exponential function, our base can be anything that's a positive value. But let's take a look at the exponential function where your base is e, which is that number that's between 2 and 3. Okay, so if I have f of x equals e to the power of x, that's exponential growth. And so you get familiar with the way it looks on a graph. And of course, I'm sure you're familiar with it. You just have to recall it. Now remember, unless it's shifted, this graph is crossing. Yeah, it has 1 point, which is 0, 1. And the same with exponential decay, which is f of x equals e to the power of negative x, which could be also written. Let me just write it in a different way so you can connect the dots here. So I can also write this function exponential decay as f of x equals 1 over e to the power of x, right? Okay, and again, it also crosses y-axis at this particular point, 0, 1. And it has this x-axis as an asymptote, so to speak, And of course, you can shift it up and down to the left or to the right, but unless this is called generic or parent function, and then from there you can learn about the shifts. And in this class, you can use a calculator if you cannot visualize something to graph something with TI-83 384. All right, and let's take a look at natural logarithm. So natural logarithm definitions of ln of x is the same as log base e of x. And so for short notation, we just don't write log base e of x, we just write ln of x. And the relationship between logarithmic function and exponential function, they are inverses of each other. Now, you have probably seen this before, not probably, for sure, you should have seen it before. How to rewrite any logarithmic expression in exponential form and exponential expression in logarithmic form. So here's the definition right here from your textbook, from previous class. Y equals ln of x. Given this equation, I can rewrite it in exponential form. It's equivalent to e to the power of y equals x. Now, the general rule here is below. It really says the same thing, but I just changed the symbols for maybe for memory here. I use P, B, and A. P for power. Let me actually write it down, but because it's more memorable. P, power, and I specifically don't want to use the word exponent here. Uh, B, base, and A will be answer. So take a look. If I take here, if I take base to some kind of power, gives me an answer. That is well, of course, B has to be restricted to a positive value here. So we have to be kind of, I'm assuming that you already know all the little details here. And A also have to be a positive value. But so I'm using this PB and A for memory help here. So if I take some base, bring it to a certain power, it gives me an answer. We are familiar with these expressions, these exponential expressions. Now, if I had to rewrite it in terms of logs, take a look. Here it is. Take log base B of answer, it gives you power. So that relationship is a little more memorable. But anyway, both of these expressions say the same thing. And your job is to remember how to convert between the bases and base form, logarithmic form, and exponential form. Now I'm gonna, there's gonna be a couple examples to follow. How do you do that? But I am confident that you've done it before, so hopefully it's a review for you. Well, let's take a look at the first, four examples, and let's first try to rewrite it in a different form. So I'm looking at a ln of e to the power of 3. How can I write it in exponential form? Well, take a look. Isn't this the same as really log base e of e to the power of 3, right? It's log base e. So what I'm gonna do, I'm gonna write it in exponential form using different colors for clarity here. So my base is e to what power? And remember, we really don't have this, right? To what power? I'm putting question mark here, and actually let me erase this. Erase this and put question mark there as well. Okay, so that's what we are trying to find out. So base e to what power gives me this for an answer, e to the power of 3. And you can already, you don't really need to solve it. Think about it, it's equation. So I have to replace my question mark with what? With 3. Okay, so that's it. This question mark should equal to 3. Okay, let's take a look at the second one. Again, I want to rewrite. We are trying to evaluate to see what it's equal to. So that's what we are trying to, oops, different color, different, that's what we're trying to find. Okay, I want you to think of this as log base e of 1, right? And then we are thinking of what is it equal to. Again, rewriting this in terms of this exponential expression. So that's my base e to what power will give me 1. Okay, and you have to think through your algebra knowledge. What would give you 1? Bringing something like 2.7 something, or some positive value, or even a negative value, to what power would give you 1? Well, that equal sign, if you call algebra, you should equal to 0. Anything brought to a power of 0 gives you 1, except 0 itself. 0 to the power of 0 is undefined, but everything else to the power of 0 is 1, so that your question mark should be 0. All right, let's do the same thing with the next one. Again, I'm going to rewrite this in the first. Again, we're trying to evaluate, but without really using calculator, kind of thinking through this. Well, what does it mean? What we are trying to answer here. Okay, I have log base e of 5, and I'm trying to see what it equals to. Right, writing it in exponential form, I have base e to what power will give me 5. And so, if even though it's written correctly, we cannot really guess in our mind what power e 2.7 something brought to what power is going to give you 5. It's not going to be a very nice number like integer. So, in this case, in order for us to figure out the answer to this, we just have to plug it into the calculator, literally find the key and type it ln of 5 and see. You have to evaluate it with calculator, and the calculation should give you something like 1.609 rounded. This is 1.609, and I'm putting that up because we rounded here. All right, so with the first two you could kind of figure out without a calculator. With the second one you had to think just a little bit. And the last ln of 0.01, well, we could write it as e. Oops, let me use the different color here. We could write it as e to what power would give me 0.01 for an answer. It's not, we can write it, it's correct, but we cannot really solve it. So in this case, again, we have to just plug it in the calculator, um, and find approximation. So we're typing ln of 0.01, and each the calculation should give you something like, let's see, it should be negative 4.605. Again, it's rounded. Okay, so I was trying to focus on how we rewrite a logarithmic expression, specifically here with base e, which is ln of x. How can we rewrite it in exponential form? And then, how can we approximate the answer, or get exact answer if we can. In the first two cases, a, b, you could just rewrite and figure out the answer. In the second two cases, c and d, you have to use a calculator to approximate. Alright, and now let's take a look at the property of natural logarithms. You are supposed to be familiar with them because you've done them in prerequisite class, but our job here is to refresh our memories. So I'm listing them, labeling them, 1, 2, 3, 4, 5, 6, 7, 8. Please take a look, make sure they are familiar. So the first one is you have ln of something that's multiplied, a product. Okay, could be m times n times other things. So if you have the product, a log of a product, you can break it into two terms, so to speak, or two items that are connected by plus while using the same log, the same base. Then take a look at property number two. If you have a ln or log of some quotient, something divided, right? You can break it also into two items, but whatever was in denominator is going to be subtracted, but you also keep the same log. So you can break it into two pieces if you have a quotient. Sometimes you have more things involved. You can have multiplication and division. You have to use these properties simultaneously together. Then the third one is when you have ln of something to the power. Then you can bring that power in front of log. Then the fourth property you should be familiar is natural log of e is equal to 1. It's basically e to what power would give you e for an answer. And here the question mark is supposed to be 1. So that is a property that you're supposed to memorize. Then property 6 is log base b. It is a conversion formula. So you could have log of any base. So base b of m. How would you even put it in calculator if, let's say, it was log base 5 of let's say 70? Well, you could rewrite it in this form. It's a conversion. So log base b of m, it could be written as this ratio, ln of m over ln of b. And similarly, if you have natural log of m, then you can write it as this ratio, ln log of m over log of e. And if we don't write anything as a subscript by the log, that means it's base 10. Okay, so that's property number 6. Number 7, you have ln of e to the x. Well, that's equals to x. And then you have e to the power of ln of x equals to x. Make sure that x is greater than 0. It's positive value. Let's take a look at some examples where you are given information. You're given that ln of 2 is equal to 0.6931 and ln of 3 equals to 1.0986. Your job is to figure out what's ln of 6 and ln of 81. All right, so let's continue and replace. First of all, use the property here. ln of 6 can be written as ln of so we agree that 6 is the same as 2 times 3, right? So it's technically I have ln of product 2 times 3. So I'm going to write ln of 2 plus ln of 3. I am using property number 1, and then I'm replacing obviously ln of 2 with 0.6931. Then there's plus, and ln of 3 is given as 1.0986. Put it in calculator and you got the answer. Okay, let's take a look at this B part. You need to simplify ln of 81. 81 can be written in so many different ways. Like when you think of 81, you're thinking maybe as 9 times 9 or 9 square. But I don't know what's ln of 9. I mean, I could convert, I can do several steps here, but can I express 81 in terms of um, 3 or 2? So 3 to the power of 4, if you check on your calculator, is equals to 81. So that's convenient because I already know what's log of 3. So I'm gonna rewrite, let me change the color so it's consistent here. So I'm gonna rewrite this as ln of 3 to the power of 4. And then I'm just using property number 3 where I have exponent, and I'm going to write this exponent in front, and ln of 3. And of course, we can replace ln of 3. I'm gonna have 4. ln of 3 was given us, let's put parentheses, 1.0986. Put it in a calculator and you got the answer. Let's do a couple more. Let's do D. And this one is find ln of 2e to the power of 5. Okay, again, same idea. We need to use property here. You cannot just put it in a calculator. If you put it in calculator, it's going to be different because remember they gave you the values ln of 2, ln of 3, and they have rounded them. So putting calculator is going to give you a wrong answer if you just put it. I mean, it's going to be correct answer, but it's going to be wrong uh, comparing to the information that was given. It's actually going to be close, but not quite the same. All right, so let's continue with this. And I already see 2 times e to the power 5, and we want to break it into 2 using property number 1. So it's going to be ln of 2 plus ln of e to the power of 5. And doing one more time, I am gonna break this ln of e to the power of 5 using property number 3. So it gives me ln of 2 plus 5 times ln of e. And of course, we already have, oh, we do have to remember that ln of e equals to 1, right? This is property number 4. This equals to 1. And you're left with ln of 2 can be replaced as 0.6931 plus 5 times 1, and it should give you, if you plug it in the calculator, you're gonna get the number. Okay, let's do one more, and that's gonna be e. Okay, let's do log base 2 of 3, and here what I'm going to use property number 6, which is log, oh gosh, let's see, so it's log, somehow I need to correct the messiness there, but it's log base so log base 2 of 3, we can write it as a ratio ln of 3 over ln of 2, and we know what's ln of 3. Let's replace it with what's given. ln of 3 was 1.0986 divided by ln of 2, which is 0.6931. Put it in a calculator and you got the answer. Okay, let me correct the messiness there. And okay, so again I fixed property of 6, and then let's move on to some other examples. And now let's take a look at your exponential and logarithmic functions. So they are inverses of each other. Looking a blue curve, this is your e to the x, g of x equals e to the x, it's exponential, and it's if you take and reflect that curve over y equals x dotted line, y equal x equation, you will get this green curve, which is f of x equals ln of x, which is your natural logarithmic function. And take a look at their similarity. Again, they're literally a reflection of each other over y equals x. They do have a point of intercept, so e to the power of x exponential function intercept y-axis at 0, 1, and logarithmic function intercepts x-axis at 1, 0. They are inverses of each other, pay attention to the domain. If you look at the blue curve, the domain is between negative infinity to positive infinity, and domain of the f of x equals ln of x is from 0 to infinity. All right, and then let's solve the following equation, f of x equals ln of 5 minus 2x. Now remember, 5 minus 2x have to be um, greater than 0, right? We cannot have ln of some negative number or even of 0. So we set up, we actually here we are not solving, you're finding domain. So we set up 5 minus 2x is greater than 0 as an equality. And you, of course, you subtract 5 from both sides like you would in equation. You are interested in isolating the variable. So subtract 5 from both sides. All right, and you got negative 2x is greater than negative 5. And then you're going to divide both sides by negative 2. But remember, this is inequality. It works similar to equation, but not exactly the same. So when you divide or multiply by a negative value, you switch the sign of inequality. It's very important to remember. Okay, so negative 2 divided by negative 2 goes away as 1. You got x left on the left side, and you have negative 5. Oops, you should have your negative or negative, you should have a positive 5 over 2. All right, and so the domain is from everything that's less than positive 5 over 2. I need to correct that again. That should be positive 5 over 2. Okay, so this is how you find the domain of logarithmic function. Now, do not mix those round parentheses and square brackets. So round parentheses says that this endpoint 5 over 2 is not included. Okay, square brackets, it's if you want it included, but then I would have to have something like equal sign alone with inequality. Just wanted to make sure you remember that. All right, let's take a look at how we solve exponential and logarithmic equations. So here, example, solve e to the power of 3x equals 2. Okay, so and first of all, there is different methodology. I could have, let's say, taken this expression and rewritten it in logarithmic form, but or I could take natural log of both sides. I can actually take any log of both sides as long as I do it to both sides. But natural logs make sense because I see in the equation. So I'm taking natural log of both sides. Okay, so left and right, and then of course use the property. You have ln of e to some power. You use the property, bring the power in front. 3x is in exponent in your expression here, ln of this expression. So 3x comes in front of ln of e. And just right side is ln of 2. Now, we already know the property. We know what ln of e is. It's, again, using the properties. And we're just replacing this with 1. So on the left side, you're going to have 3x times 1, or just 3x. And on the right side, you still have ln of 2, which is a number. There's no variable there. Now you're trying to solve for x, so you want to isolate x. How do we do that? Divide by 3 both sides. So 3 divided by 3 cancels, obviously, but I do want to mention something here, that ln of 2 divided by 3 is not the same. It does not equal to ln of 2. You cannot really change this to ratio like that. That's most common mistakes that students make, and I just want to mention that. ln of 2 is already a number itself. Okay, so then of course cancel 3. You got x equals ln of 2 over 3. And that is already an exact answer. If you were asked for an exact answer, that's it. But if you needed to put this in a calculator and approximate, then you just plug it in a calculator and find ln of 2, then divide by 3, and you should get something like x is approximately equal to 0.231, and that's rounded. And you can always check if you are, especially if you're on exam or on a quiz, you want to check if you solved it correctly. You put that x back into the equation. But remember here, we are approximating, so I'm expecting, the left side to be approximately 2, but not exactly 2. So check to make sure that's approximately 2. All right, let's take a look at another example B. And here's 250 e to the power of 0.015 times t equals 750. Okay, we are solving equation here. Now I see that I have e to the power of something with variable times 250. Well, I'm trying to clean it up, so divide by 250 both sides because it's just a factor. So remember, it's equations, you do it to both sides. Divide by 250. It cancels on the left side, and you got just e to the power of 0.015t equals to, and we can simplify, at least it's 75 divided by 25, and can simplify a little further, it equals to 3. Okay, so now you have variable on the left side. You have e to the power of 0.15t equals to 3. And you do the same thing you did in example A. You will take natural log of both sides and then use the properties just like we did before. So taking ln of the left side and ln of the right side. Don't forget this equation, whatever you do one side, you have to do to the other side. And then since my variable is in exponent and I have this property where I can move this exponent in front of ln, so we are moving it in front of ln, and then I got 0.015t times ln of e. And we like ln of e because it equals to 1, right? According to our property. On the right side, I have ln of 3. So ln of e, it shows up now as 1. Okay, so and then I'm back to a simple equation. 0.015 times t equals ln of 3. ln of 3 is already a number. There's no variable there. We divide by 0.015 both sides to clean up the equation and leave t by itself on the left. And on the right side, I have ln of 3 over 0.015. This is already exact answer. But if I needed approximation, we would plug this in a calculator. ln of 3. Put ln of 3 in parentheses when you are using calculator. I'm gonna add the parentheses here so you guys remember. And then, so I would put ln of 3 divide by 0.015 to make sure that I got the correct answer. All right, and there's our approximation, 73.24. And let's take a look at the following example. Marissa invests $12,000 in an account earning 2.8% annual interest compounded continuously. When will Marissa's account double in value? Okay, so we use our continuous compounding functions that you already know from the previous class or you've seen it earlier, and we just plug in the number. The principal is 12,000. It's e to the power of 0.028. Make sure you write as a decimal, right? It's 2.8% times t. Okay, and then we want to double 12,000. So obviously on the left side, the output is going to be 24,000, right? Just copying everything with t, and then how would we solve it? We already know how to solve this. We would divide both sides by 12,000 to clear up the equation, right? Eventually, you want to get to t by itself. So dividing by initial principal, 12,000, it gives you on the left side, you just get 2. On the right side, the principal is completely gone. Their initial value is completely gone. You get e to the power 0.028t. Now, how do we solve this? We take natural log of both sides, and just like we did with the previous example. But this is a key or classic example. How do you uh, have something doubled? Okay, so I just want to make sure that we capture this idea that if my to double something, I take initial principal, and then my answer, my output, my final value is 2 times the principal, right? But then when we solve it, we divide the principal out, and you get 2 equals e to whatever rate, and times t. So that's a general procedure, and it's going to be the same. By the way, it's going to be the same if you want to triple something. You just change 2 to 3, right? Because you're tripling the principal. But it's the same idea. The process is the same. All right, so then let's take a natural log of both sides and solve it. Got ln of 2 here, and we already know we're going to have ln of e to the power of 0.028t. Then we bring our, on the left side we already have a number, but on the right side, remember, we bring our power exponent in front of log, which contains the variable t, which we are trying to solve for, times ln of e. We already remember what ln of e is. It is equal to 1. And so I have ln of 2 on the left and 0.028t on the right. And we're solving for t, so we divide both sides by 0.028. And t is going to equal to, yeah, that's our exact answer. If you wanted to approximate, you plug it in the calculator. Approximation is 24.8 years. Okay, now when we look at this general process, we need to kind of remember this in the following way. So I'm repeating myself here. So you have a principle, you double something. Your output is 2p, all right? To e to the power rt. We're using our continuous compounding formula. Now then you cancel p because you divide both sides by p, and you get 2 equals e to the power rt. That's this. And then of course you take ln of 2, you take ln of both sides, and brings you to ln of 2 equals rt. Just look at this, and the solution is t equals ln of 2 over r. Okay, we already kind of walked through this, and it's going to be the same over and over. It leads us to the following formulas. If you pay attention here in the formulas, we are talking about the same time, but in the formulas we switch to capital T. So you have R times capital T equals ln of 2. And you can use this equation and solve for for different variables. You can solve for R, you can solve for T. It's derived from this process. So you don't always have to go through this process. As long as you are given rate or time, and you know you want to double something, you know it's continuous compounding, then you just bypass all the step of solving equations. I mean, you could still go through the steps if you want, or you could use these shortcut formulas. So if I'm looking for t, I'm gonna use the last one. If I'm looking for r, I'm gonna use this second one, ln of 2 over t, and and there you go. It's a basic shortcuts. I need to memorize them because they're easy, they're simple, or have them in front of you when you solve equations or solve word problems. Let's take a look at the following. Solve 2 plus 3 ln x minus 1 equals 8. Okay, remember we need x minus 1 a positive value, right? Otherwise, the equation is undefined. So we solve this equation as a normal equation by cleaning up the 2. So subtract 2 from both sides because it was added right on the left. Then I'm left with, on the left, with 3 times ln of x minus 1. It's in parentheses. Keep the parentheses straight because it's different than ln of x minus 1 or ln of x minus 1. So on the left side, I have, on the right side, I have 6. On the left side, I have 3 times ln of x minus 1 in parentheses. Okay, then remember left side is multiplied times 3, so to undo that we divide by 3 and always divide both sides. It's an equation, right? So you divide left side to get rid of 3. It goes away as 1. 3 divided by 3 is 1. And you're left with ln of x minus 1 on the left, and you're left with 2 on the right. And at this point, you can rewrite this expression in exponential form. You have base e to the power of 2 equals x minus 1. Base to the power gives you answer. It's that little trick, the memory trick that I left in the previous on a previous page. Remember, natural log of something, it's log base e of something, and we know how to rewrite it in the exponential form. So it's e to the power of 2 equals x minus 1. All I'm doing, I'm rewriting logarithmic expression in exponential form. And I don't need parentheses anymore on the right because it's just 2 items there. Okay, but then we are solving for x. We want x by itself. So what do? We add 1 to both sides. And you got x by itself now on the right, and you have e to the power 2 plus 1 on the left. And this is already an exact answer. That's it. But sometimes you need to approximate it. And we have to make sure that it is the value that we got is in the domain. We got 8.389 approximately. Okay, is it in our domain? So what is the domain of this? Remember, x minus 1 has to be greater than 0. So we have to make sure that our answer is in the domain. So we solve this little inequality. X is supposed to be greater than 1, and 8.389 is definitely greater than 1. So domain is from 1 to positive infinity, and that value fits in. Remember, in logarithmic functions, you could have one solution, you could have no solution, you can have several solution. Our solution here is valid solution. Okay, so make sure you always check with a logarithmic function to make sure you got the valid solution. Hopefully it is a review for you guys from the previous prerequisite classes.